this video lecture, we are going to first see an example which is related to linear transformations. Suppose we are considering two vectors, alpha 1 is equal to ordered pair 1 2 and alpha 2 is equal to ordered pair 3 4. Okay. Basically, first we are going to say that it is a linearly independent subset of the vector space R2 over R. For that, what we should do, first we should equate this linear combination of alpha 1 and alpha 2, which is say C1 alpha 1 plus C2 alpha 2 is equal to 0. Then you get C1 into ordered pair 1 2 plus C2 into ordered pair 3 4 is equal to 0, implies C1 plus 3 C2 is equal to 0 and 2 C1 plus 4 C2 is equal to 0, or it can be represented in the matrix format C1 C2 into the matrix 1 2 3 4, that is equal to 0 0, and it is a system of linear equations, and we can solve for C1 and C2 like this, and you get C1 is equal to 0, C2 is equal to 0. That means the two elements 1 2 and 3 4, ordered pair 1 2 and ordered pair 3 4 are linearly independent, right? And also at times there is a useful result, which is nothing but, suppose we had written the matrix format of the system of linear equations. Suppose if the matrix 1 2 3 4, the 2 by 2 matrix is invertible, then you can find the column vector C1 C2 to be equal to the inverse of the matrix 1 2 3 4 into the matrix with matrix multiplication into the column vector 0 0, and you obtain the column vector 0 0, which means C1 is equal to 0 and C2 is equal to 0. So when we understand that the matrix, the coefficient matrix here is invertible, you can correspondingly say that C1 is equal to 0 and C2 is equal to 0. That means the elements which we had taken is the set of the two elements will be linearly independent. We can conclude that using this. So we got that the two elements, ordered pair 1 2 and ordered pair 3 4, are linearly independent, and since the dimension of R2 over R, that means the number of elements of the basis, is equal to 2, we can understand that this set is also basis of R2 from earlier theorem. So now that we have this is also a basis of R2. Okay. Now consider T of 1 0. Okay. T of 1 0 can be written as T of this 1 0, the element can be written as a linear combination of the elements in the basis, right? So 1 0 can be written as C1 into 1 2 plus C2 into 3 4. Okay. So from that we have to find what is C1 and C2, right? So suppose we have the corresponding linear combination C1 1 2 plus C2 3 4 is equal to ordered pair 1 0. From that you can form a system of linear equations, and you can see here how to solve the C1 and C2. Here you will obtain C1 is equal to -2 and C2 is equal to 1. You can substitute that here. Okay. And also, since T is a linear transformation, we had taken, suppose if we are taken T, the function T to be a linear transformation, you get C1 into T of 1 2 plus C2 into T of 3 4. And in the example we are given that from the earlier theorem, that if alpha 1 and alpha 2 are forming the set of bases for R2, then there will exist a unique linear transformation from R2 to R3 such that T of alpha 1 is mapped to this element and T of alpha 2 is mapped to this element. This we had proved in the last class in the video. So we are applying what we are getting here. T of alpha 1, it is given as the order triple 3 2 1. T of alpha 2 is the order triple 6 5 4. So you get it, and you know what is C1 and C2. Substitute it. You get T of 1 0 is equal to order triple 0 1 2. That is example 6. In example 7 says that if T is a linear transformation from Fm into Fn, we know that there exists linear transformation from Fm to Fn such that the vectors beta 1, beta 2, etc., beta m are considered, then the corresponding images of the standard basis, elements in the standard basis, that is T of epsilon 1 is equal to beta 1, T of epsilon 2 is equal to beta 2, etc., T of epsilon m is equal to beta m. Like that we can have a transformation T, which we mentioned before. The same theorem applies here. And we said that T is a uniquely determined transformation. Okay, and suppose if alpha is equal to the ordered m tuple x1 etc. xm is an element from Fm. So this alpha can be written as the linear combination of the standard basis. So you have x1 epsilon 1 plus x2 epsilon 2 plus etc. plus xm epsilon n, and applying t on alpha, you get T of alpha is equal to T of x1 epsilon 1 plus x2 epsilon 2 plus etc. plus xm epsilon m. And with the property of linear transformation, you get that to be equal to x1 into T of epsilon 1 plus x2 into T of epsilon 2 plus etc. plus xm into T of epsilon m. And we know that T of epsilon 1 is beta 1, T of epsilon 2 is beta 2, etc. T of epsilon m is beta m. So that's how you end up here. Now it also can be represented like this. If beta is an m by n matrix having the row vectors beta 1 etc. beta m, T of alpha is equal to alpha into a beta. That's how we can arrange it in the matrix form. Or in another words, if beta I is equal to capital bi1 etc. capital bin, then T of the row vector x1 etc. xn is equal to the row vector x1 x2 etc. xm into the matrix format written here. You can understand that from the whereabouts which we discussed earlier logically. Okay, suppose if T is a linear transformation from V to W, then the range of T is actually a subset of W, right? If T is a function from V to W, we know that T of V is contained in W. We have to prove that this T of V is a subspace of W, and this T of V is also written as denoted as R suffix T. It is nothing but the set of all beta in W such that beta is equal to T of alpha for some alpha belongs to V. So for that, take two elements inside RT and C be a scalar. Then the two elements beta 1 and beta 2 can be written as T of alpha 1 and T of alpha 2 for some elements alpha 1 and alpha 2 in V, right? Here alpha 1 and alpha 2 are inside V for some V. For some alpha 1 and alpha 2 in V, consider C into beta 1 plus beta 2, that will be equal to C into T of alpha 1 plus T of alpha 2, that is equal to T of C alpha 1 plus alpha 2 by the property of linear transformation. And definitely this element is written as T of something, and this something is clearly inside V. So you have this element to be contained in RT, which is the range of T. So that means the range of T is not only a subset of W but also a subspace of W. And also another subspace is there which is called the null space. This set is denoted by capital N, which is nothing but the set of alpha in V such that T of alpha is equal to 0. That means all the elements inside the domain which are mapped to 0, right? This is also subspace of V. This is definitely this is a subset of V. We are going to say that it is a subspace. So because we have T of 0 is equal to 0, that means 0 is inside that. And suppose if T of alpha, if alpha 1 and alpha 2 are belonging to, suppose if alpha 1 and alpha 2 are belonging to N, then you know that T of alpha 1 is equal to T of alpha 2, which is equal to 0 because it is in N, right? Now we have to prove that C alpha 1 plus alpha 2 belongs to N. For that, consider T of C alpha 1 plus alpha 2, that is equal to C into T of alpha 1 plus T of alpha 2, that is equal to C into 0 plus 0, and you get totally 0, which means that this element C alpha 1 plus alpha 2 belongs to N. So if from this you can define the simple definitions. Suppose if V and W are vector spaces over the field F and T is a linear transformation from V to W, the null space of T is a set of all vectors alpha in V such that T of alpha is equal to 0. Okay. And if V is finite dimensional, the rank of T is the dimension of the range of T, and nullity of T is the dimension of the null space of T. So you defined three terms. One is the range space, the other is the null space, and then you defined rank, which is equal to the dimension of the range space, and nullity, which is equal to the dimension of the null space. And from all these terms, we are going to frame theorem 2, which is also a simple theorem, and it's one of the most important results in linear algebra, and it is called as the rank nullity theorem. So rank nullity theorem states that if V and W are vector spaces over the field F and T is a linear transformation from V into W, and suppose if V is finite dimensional, okay, then rank of T plus nullity of T is equal to dimension of V. Proof. Suppose if alpha 1, alpha 2, etc. alpha k is forming a basis for the null space N, okay, which is N is denoted to be the null space of T. And since this N is a subspace of V, we know that this basis can be extended by adding some more vectors, say alpha k plus 1, etc. alpha n, along with it, such that the set alpha 1, alpha 2, etc. alpha k, comma alpha k plus 1, comma etc. alpha n is forming a basis for V. And now we are going to claim that T of alpha k plus 1, comma etc. comma T of alpha n is a basis for the range of T. Okay. So first, from the first lines of the proof, we get that nullity, which is equal to the dimension of the null space of T, is equal to k. We have assumed it. And also we are assuming that the dimension of V is equal to n. If we are assuming that, then we said that the basis elements of the null space of T can be extended by adding some more vectors, alpha k plus 1 till alpha n, such that all of alpha 1, alpha 2, etc. alpha k plus 1, etc. alpha n is forming a basis for V. That means dimension of V is equal to n is satisfied. And then we are going to claim this, that the range of T is having the basis T of alpha k plus 1, etc. alpha n. So first we have to prove that they span. So consider we are knowing that alpha 1, alpha 2, etc. Alpha k belongs to the null space, right? So when we consider T of alpha j, we know that T of alpha 1, T of alpha 2, etc. T of alpha k all are zeros. So we can generally say that T of alpha j is equal to 0 for all j less than or equal to k. Right. So consider a beta, which is an element inside the range space. Okay, suppose if beta belongs to range space, okay, then beta okay to prove that, take an element beta in RT, then beta is equal to some T of alpha, right, because it is in the range space for some alpha belongs to V. So that is equal to T of alpha can be written as the linear combination of the basis elements. So we are saying that suppose if that is equal to C1 alpha 1 plus C2 alpha 2 plus etc. plus Cn alpha n, So that is equal to C1 into T of alpha 1 plus C2 into T of alpha 2 plus etc. plus Cn into T of alpha n. Right. So you got that. So since this beta is equal to C1 into T of alpha 1 plus C2 into T of alpha 2 plus etc. plus Ck into T of alpha k plus Ck plus 1 into T of alpha k plus 1 plus etc. plus Cn into T of alpha n. But we know that till k, T of alpha 1, T of alpha 2, etc. T of alpha n is equal to 0, right? So this beta is equal to Ck plus 1, T of alpha k plus 1 plus etc. plus Cn T of alpha n. That means for any arbitrary beta that is happening inside, that is inside range space, this beta can be written as a linear combination of T of alpha k plus 1 etc. T of alpha n. So that means the set of all elements T of alpha k plus 1 etc. T of alpha n sitting here will span the range space. So our first claim is proved. Then we have to prove the second claim, which is that these elements are linearly independent. For that, what we have to do? We have to take the linear combination of the elements and equate it to 0. And since we have taken T to be a linear transformation, by its property we know that that will imply T of the term sitting here is equal to 0, and that will necessarily imply whatever that is sitting inside this T, that element, that term belongs to the null space of T. Okay, and we know that apply, so you get this C of, that is an element inside the null space, right? So we get that, yes, the elements inside the null space can be written as a linear combination of alpha 1, alpha 2, etc. alpha k. So this element inside the null space can be written as some scalar b1 alpha 1 plus b2 alpha 2 plus etc. bk alpha k, because alpha 1, alpha 2, etc. alpha k form the basis of the null space of T. Simple. So just rearrange, you get these much terms is equal to 0. But alpha 1, alpha 2, alpha k plus 1, etc. alpha n is a basis of V. So they are linearly independent. That means beta 1, beta 2, etc. beta k simultaneously minus Ck plus 1, etc. minus Cn is equal to 0. That means Ck plus 1, Ck plus 2, etc. Cn is equal to 0. So you get, we assumed this, and we obtained Ck plus 1, Ck plus 2 equal to etc. equal to Cn is equal to 0. That means T of alpha k plus 1, T of alpha k plus 2, etc. T of alpha n are linearly independent. So they form a basis of range space, because we prove the two claims that this set of elements spans the whole of the range space as well as they are linearly independent. Now you have to prove theorem 3, which says that if A is an m by n matrix with entries in the field F, then row rank of A is equal to column rank of A. So suppose if T is a linear transformation from, to prove it, suppose if T is a linear transformation from R n plus 1 to, or call it yes, call it F to F m plus 1. Okay, and define it as such that T of x is equal to Ax, where x is an n by 1 matrix, and here A will be an m by n matrix. Okay. The null space of T is a solution space of the system Ax is equal to 0, right? Let me call it n. N is equal to set of all elements x such that where x in fn plus 1 such that ax is equal to 0. So that is the set of all column matrices x such that ax is equal to 0. Similarly, the range space is equal to set of all y such that ax is equal to y is equal to y. So if a1, a2, etc. an are columns of A, then ax can be written as x1 a1 plus x2 a2 etc. xn an, right? Say suppose if I am writing ax, okay. So we are saying that a is the column a1, a2. This is the first column. This is the second column, etc. an, the nth column. Into here we have x1, x2, etc. xn. So if it happens to be like this, you can say that it is nothing but x1 into a1 plus x2 into a2 plus etc. plus xn into an, right? So that means the range of t, uh, which is this, y is equal to ax. So this is y, right? So this y is actually spanned by the columns of A. In other words, we can say that the range of T is the column space of A. That means the dimension of the range of T, which is the rank of T, is equal to the dimension of the column space of A, which is the column rank of A. And from the rank nullity theorem, we know that dimension of S plus column rank of A is equal to N. And you can refer the example 15 of chapter 2, which is related to matrices, and that will end up with the conclusion that the solution space S has a basis consisting of n minus r vectors. So that means dimension of S is equal to n minus row rank of A, and when you compare, you are going to get that row rank of A is equal to column rank of A. And hope you are getting an outline of this theorem, and you prove it out rigorously and solve the rigorous part and work out the exercises too. So thank you for watching out this video. See you in the next video lecture. Till then, bye.